In this video, we are going to discuss ionic radii and ionic strength and how they relate to some new word that we're going to learn about called activity. So to begin with, what do I mean by ionic radii? So you've got sodium shown in this picture and it's positively charged. If you place sodium into solution, it's going to have a hydrated radii that is different than its ionic radius. So its ionic radius is going to be dependent upon the structure of the atom. The hydrated radii is going to appear because you have water molecules in solution, and the water is going to orient itself such as you see here in this picture, where the partial negative parts of water, that being the oxygen, are oriented toward the sodium's positive charge. If you were to put a negative ion into solution, the positive hydrogen parts of water are going to be oriented toward that negative ion. And so you end up with a radius for sodium ions that is actually larger than the ionic radius of sodium itself. It's called a hydrated radii, and you can see lots of examples here on the right-hand side of your screen. Let's look at this example here of iron thiocyanate. So if you have iron, just iron 3+, it's going to be a yellow, like you see here on the left in the left beaker. But whenever you mix it and the reaction goes forward to equilibrium, you'll produce iron thiocyanate, which is a red color. And so you can see the equilibrium expression here on the right-hand side. Well, my big question is, what does this have to do with ionic radius, hydrated radius, all of those words? Well, a lot, because something really cool happens if you add in a salt that's supposed to be inert. Inert means like non-reactive, right? And so potassium nitrate is not going to react with iron thiocyanate. But yet, something still happens that is quite fun to look at in solution. So in this figure, you see two solutions that are made the exact same way. They both contain the iron 3 thiocyanate. They are nice, pretty red. But we're going to add in potassium nitrate to just the beaker on the right and watch what happens. It's now yellow again. Why in the world would adding potassium nitrate to iron thiocyanate change the color back to its original unreacted version? So look back at the reaction at the top. Something appears to have happened that shifts from our product to our reactants. And so we have shifted our equilibrium to the left. Why did this happen just simply by throwing in a salt that we already said wasn't reacting? Well, when you throw potassium nitrate into solution, your potassium is going to find all the thiocyanate and kind of hydrate it, just like your water was shown in the previous slide. Your nitrate is going to be negatively charged, so it's going to surround your positive ions. And so is iron going to find thiocyanate as often as it might have? No. And so you're going to have a whole lot more of iron 3+ dissolved in solution and not forming product. Your reaction has shifted to the left, but it's done that because you've added in a salt, which increases the ionic strength of your solution. Ionic strength just simply being a fancy word that says, how salty is your solution, not accounting for your analyte. And so when we did this, you change your equilibrium just slightly and it's adjusted. And so in general chemistry, you may never even consider the fact that there might be a salt in your solution. In quant, we're going to consider the salts that may or may not be present and think about how they affect equilibrium. In this graph, you can see that they did that exact same thing where they wanted to graph the equilibrium constant on the y-axis as a relationship to the amount of potassium nitrate added. And so you can see the highest K values happen when there is no salt, when there is no potassium nitrate. The more potassium nitrate you add, you can see that the equilibrium constants decrease. Now, what are we saying happens when you decrease K? We're decreasing our product, that of our iron 3 thiocyanate. So when we decrease it, we're shifting it to the left, which is exactly what we saw and thought through in the previous slide. And so equilibrium is going to change based on the presence or absence of a salt. Here's another similar case to this. Here we have calcium sulfate. And if we add ions in the form of potassium nitrate, we're increasing the ionic strength of a solution. Adding a salt increases ionic strength. This changes those ionic atmospheres, okay? It increases that radius that you see because now your calcium is surrounded by nitrates and your sulfates are surrounded by potassium ions. And so what that means is your potassium and your sulfates are not going to find each other as much, which means they are going to stay as ions instead of as the product of calcium sulfate. So in this case, potassium sulfate is going to become more soluble because Every calcium and sulfate that's thrown into solution as calcium sulfate, as soon as they break apart, they're not going to find each other as quickly. And so they're going to become more soluble in solution. And so this is a case where if you've got some analyte that you're trying to make soluble, you can just throw in extra salt and it becomes more soluble. Next, I want to think through the concepts that are shown in this figure. There's a lot to this figure. So what we see on the left-hand side is potassium hydrogen tartrate solubility. And so the structure of that compound is shown on the left. It's an ionic compound with a potassium cation. And then on the right-hand side, we have the concentration. On the x-axis, we have the concentration of each substance added. And so either we added glucose, sodium chloride, magnesium sulfate, or potassium chloride to our solution of potassium hydrogen tartrate. And we look to see how did the solubility of the species change as we added more and more of that substance to the solution. So let's look at glucose first. If we add glucose to the substance, we don't really see a change in the solubility of potassium hydrogen tartrate. Why not? Glucose is not an ionic compound, and so it doesn't break apart into solution, and it's not going to form those increased ionic radiuses that we talked about earlier. And so because of that, it has no real large effect on the solubility of potassium hydrogen tartrate. So that's kind of your middle. But then look, we added sodium chloride. Sodium chloride is ionic, it breaks apart. It affects the solubility quite a lot. Add in more sodium chloride, the solubility goes up. Why? Because your cation and your anion cannot find each other in solution, so they become more readily dissolved. What about magnesium sulfate? How does that relate to sodium chloride? Notice it affects the solubility even more. It makes potassium hydrogen tartrate even more soluble. Why? What's different between magnesium sulfate and sodium chloride? Hopefully you realize pretty quickly that sodium chloride has a +1 and a -1, whereas magnesium has a 2+ and your sulfate has a 2-. You have increased charge. Does that lead to increased ionic radius? Absolutely. And so you're even more hydrating and surrounding that potassium hydrogen tartrate with your huge ions. And because of that now, they're even less likely to find each other in solution, so they're going to become even more soluble. But what's happening with potassium chloride? What is going on? Potassium chloride is a salt. So shouldn't it act similarly to sodium chloride? I mean, after all, they're right next to each other on the periodic table, sodium and potassium. What's going on that's different? Well, remember Le Chatelier's principle? When a change is performed to a system, the system will adjust in the direction to partially offset the change. So here is the reaction that happens when you try to dissolve potassium hydrogen tartrate into water. It produces 2 ions. What are those 2 ions? Well, you've got the hydrogen tartrate and potassium. That's the key. Why? In potassium chloride, you also have potassium. And so if I throw in extra potassium now, what direction is that going to shift equilibrium? It wants to form potassium, but when we throw in extra potassium, what we're essentially doing is shifting equilibrium to the left, because now that we've thrown in extra potassium, Le Chatelier's principle says we need to offset that change. And so how does it do it? It forms more of the solid reactant that we started with. This is called the common ion effect, because if you add a common ion, that of potassium, it's going to shift equilibrium back toward the left, thus reducing the solubility of this reaction. And so anytime you have a common ion, it's going to behave differently than just simply purely throwing in extra salts that have no effect on the reaction. So what is ionic strength? It is the symbol right here, and it is really the measure of all of the ions that are in your solution. And so when we're trying to figure out how does ionic strength affect an analyte, we first have to calculate the ionic strength, and then we can apply it to the situation of equilibrium. And so we're going to do calculations for calculating ionic strength in a later video. Then, ionic strength allows you to calculate activity coefficients, which are shown in this table. So all of the values that you see on the right-hand side, those are activity coefficients. So when you're trying to determine activity coefficients, you first have to calculate ionic strength, and then use the ionic strength and this table in order to calculate your activity coefficients. If it's not on this table, so if your ionic strength is not listed along the top there, then you can either calculate using the Dibby-Huckel equation that you see here, or you can interpolate from a table. And I will show you how to do that in a later video. Okay, so now we've used ionic strength to calculate activity coefficients. How does that change equilibrium? Well, now we've got this equation right here, and it's very important. So put a big star in it in your notes, super important. The idea is we're going to express our activity. Instead of having like your concentration of C, some species C, you're going to replace that with C times your activity coefficient. So now instead of having your equilibrium expression that looks like this, where you might have KSP equals your products over your reactants, but your product is all aqueous, your reactant is solid, so solid's not included in it. And so instead of having concentration of calcium times concentration of sulfate, your new equilibrium expression is KSP times the concentration of calcium, activity coefficient of calcium, times concentration of sulfate, activity coefficient of sulfate. So basically, anytime you saw a concentration in a prior equilibrium expression, you just add in this activity coefficient. So if we've got something like a pH equation, normally it's pH is negative log of the concentration of hydrogen. Now you sub in activity of hydrogen. And activity of hydrogen just means throw in that activity coefficient there. We're going to practice this a lot, so just kind of think through and remind yourself of this equation. But this equation, we have to get there by calculating ionic strength, determining the activity coefficient, and then we can sub it into those equilibrium problems that we already know how to do. And some quick last things to leave you with is thinking through how does the activity coefficient change based upon your ionic strength. And so as you increase your ionic strength, the activity coefficient is going to decrease. Okay, and that just kind of makes sense because as you're affecting equilibrium more, we're going to have a net effect of decreasing that concentration. Okay, and so the activity coefficient is going to go down. The next step of this is that charge plays a huge role. Look at the graph. You see how a +1 versus a 2, a 3, and a 4, those different charges are going to affect the activity coefficient differently. +1 has less of an effect than a +4. And so just the greater the charge, the more you need to correct for the ionic strength. And then the last step of this is the smaller the ion size, the more important activity becomes because you've got some small ion in solution and a huge radius around it that's going to greatly change how it interacts with other ions. And so the smaller it is, the more important these effects become. And if it's a non-ionic compound, then you can pretty well assume that you can treat these equilibrium expressions exactly how you might have done in general chemistry, and that is ignoring the activity coefficients or assuming that your activity coefficient is 1. And this is showing you kind of a good approximation for this is if the ionic strength is less than 0.1, we can pretty well assume it's 1 and we don't have to worry about it at all. So this is just an intro to the ideas and the concepts between ionic strength and activity. And we're going to practice these in depth and we're going to apply these concepts to equilibrium because basically any equilibrium problem you have done in the past, if you have any ionic species present besides your analyte, you need to consider the effects that those ions have on the ionic strength of the solution and therefore the ability of the ions to find each other in solution.